Welcome back for another deep dive. Today we're going to try to tackle a topic that's both deeply personal and incredibly vast, consciousness.
Mm-hmm.
We're going to be using Consciousness Demystified by Feinberg and Mallatt to explore this.
Great book.
Yeah, it's really good.
Really good.
We're going to explore a question that's fascinated thinkers for centuries.
Yeah.
At what point did animals go from simply reacting to the world to actually, experiencing it?
That is the question.
Right.
It's a big one.
It is.
It really gets to the heart of what it means to be alive,
Yeah.
doesn't it? I think the book does a really good job of breaking down this complex topic
Yeah.
in a way that's both scientifically rigorous and surprisingly accessible.
Yeah, I think one of the things that struck me right away was their focus on primary consciousness.
Yeah.
And I think that's a really good place to start because we could talk about, higher levels of consciousness, self-awareness,
Right.
but let's go to the very beginning.
Yeah.
Primary consciousness.
Primary consciousness.
It's not about self-awareness or complex thought,
Right.
but the most basic form of sensory experience.
Yeah.
Think of it as the ability to have any kind of feeling at all.
I like to think of it as the difference between like a robot processing information and a human being actually feeling the warmth of the sun on their skin or the joy of listening to music.
Absolutely. And it makes you realize that even those seemingly simple experiences
Yeah.
are the result of incredibly complex processes in the brain.
Right.
It's not just about sensory input. It's about how our brains interpret that input
Yeah.
and create those subjective feelings, those qualia.
Yeah, and I think that's where it gets really interesting because,
Yeah.
Feinberg and Mallatt argue that these qualia, these
Yeah.
subjective experiences,
Yeah.
are not just some like mysterious byproduct of brain activity.
Right.
They're actually deeply intertwined with the biological functions of the brain and have played a crucial role in evolution.
Okay, so how do they break down this idea of primary consciousness?
Yeah.
How do we even begin to understand what it means to have a subjective experience?
Well, they focus on three key domains of experience: exteroceptive, affective, and interoceptive.
Okay.
Exteroceptive is all about our sensory perceptions of the outside world.
Okay.
Sights, sounds, smells.
Okay.
Basically, it's like a mental movie playing in your head based on information from your senses.
So right now, my exteroceptive system is processing the sound of your voice, the sight of my notes,
Yeah.
maybe even the smell of coffee in the air.
That's a good example. Yeah,
Okay.
exactly. And it's creating an internal representation of this moment, a snapshot of your experience right now.
Got it.
Then you have the affective domain, which is all about feelings.
Okay.
Joy, sadness, fear, anger.
Right.
These are all generated by a separate system in the brain.
So this is where it gets really tricky, right? Because we can see how the brain might create a map of the external world,
Yeah,
but how do you map a feeling?
that's a great question.
Yeah.
One of the big questions they're trying to tackle in the book. They argue that just like with sensory perceptions, feelings are also rooted in physical processes in the brain.
Right.
Specific brain regions and neural pathways are responsible for generating these emotional responses.
I mean, it's got to be more than just point A to point B mapping like the optic tectum we talked about earlier.
Definitely.
I mean, emotions are a whole symphony
Yeah.
of brain activity going on.
Exactly. And that's one of the reasons why studying emotions is so challenging.
Yeah.
But even though we don't have a complete picture yet, we're starting to understand the neural basis of emotions and how they contribute to our overall experience of the world.
Okay, so we have those external senses and our internal feelings.
Yes.
What about that third domain, the interoceptive one?
That's all about our internal bodily sensations, things like hunger, thirst, pain, temperature, even that sense of your heart beating in your chest.
Okay.
It's your brain's way of monitoring your internal state and keeping everything running smoothly.
So if I put my hand on a hot stove and feel pain, that's my interoceptive system letting me know that something's wrong.
Right.
I need to pull away.
Exactly. It's a crucial system for survival
Yeah.
because it helps us detect and respond to potential threats and maintain our internal balance. And what's fascinating is that Feinberg and Mallatt argue that these internal sensations also contribute to our conscious experience, to our sense of self.
It makes sense because our bodies aren't just vessels for our brains.
Right.
They're an integral part of who we are and how we experience the world.
Precisely.
So if these three domains, the external world, our feelings
Yeah.
and our internal sensations
Right.
are the building blocks of conscious experience, can we find evidence of them in other animals?
That is the million-dollar question.
Right.
That's what we're going to try to figure out.
Yeah. Do animals actually experience the world the way we do? Do they feel joy, sadness,
All
fear?
good questions.
Yeah. How do we even begin to look for signs of consciousness in creatures that can't tell us what they're feeling?
That's where it gets tricky.
Yeah.
Well, one way is to look for something called isomorphic mapping in the brain.
Go.
It's the idea that the brain creates point-by-point representations of the world or the body,
Okay.
a kind of internal map.
Okay, follow if you will.
So, like, if my brain is processing the visual image of a tree, there's a specific pattern of neural activity that corresponds to that tree, almost like a neural fingerprint.
That's a great way to put it.
Okay.
And what's interesting is that the presence of these isomorphic maps, especially for vision, is considered a strong indicator of sensory consciousness.
Okay.
It suggests that the animal is not just passively receiving sensory input,
Right.
but actively creating an internal representation of that input.
So it's not just about having eyes, it's about having the brain power to create those mental images, those internal maps of the world. And that's why animals with complex eyes, like vertebrates, arthropods, and cephalopods, are the primary suspects when it comes to consciousness.
Yeah.
They seem to have the neural machinery to generate these intricate mental maps.
That makes sense. But just because an animal has complex eyes and can create these maps doesn't necessarily mean they're having a conscious experience, right?
You're absolutely right.
We need to look for other clues,
Yeah.
other signs that something more is going on.
For sure, and that's where behavioral observations become really important.
Okay, like what? Give me some examples.
Okay.
What kind of behaviors are we talking about?
Well, one is something called global operant conditioning.
Okay.
It's basically the ability to learn brand new complex behaviors through reward and punishment.
Okay.
Behaviors that are not part of their natural repertoire.
Okay, so if my dog learns to ring a bell to go outside,
Yeah,
that would be an example of global operant conditioning
that's a perfect example.
because it's not a natural dog behavior.
Right.
And she learned it through association and reward.
Exactly. It shows a level of flexibility and adaptability that suggests an awareness of the connection between their actions and the consequences.
Yeah.
It's not just a mindless response to a stimulus, it's a deliberate action with a goal in mind.
That's fascinating.
Yeah.
So it's not just about the physical structure of the brain,
Right?
but also about how that brain translates into actions, into choices.
Absolutely.
What other behaviors are they looking at?
Another key one is behavioral trade-offs.
Okay.
This is when animals make decisions that balance potential costs and benefits, suggesting an internal weighing of options
Okay.
and a sense of preference or value.
So like my cat choosing to stay curled up on the warm couch instead of venturing outside in the cold rain.
Yeah,
She's clearly making a choice based on her own internal sense of
right.
what's more important to her at that moment.
Yeah.
Comfort over adventure.
Exactly. And those kinds of choices suggest that something more than just basic instinct is driving their behavior. There's an internal world of preferences, motivations, and maybe even anxieties
Right.
playing into those decisions.
I'm starting to see how these seemingly simple behaviors can actually reveal a lot about what might be going on inside an animal's mind. It's like we're getting a glimpse into their subjective experience,
Yeah.
even if they can't tell us about it directly.
It is, and then there's frustration behavior, which is exactly what it sounds like.
Those
Animals reacting negatively when they're prevented from getting something they expect or desire.
Oh, I see this in my dog all the time. If I'm slow with her treat, she whines and paces and gives me those big, sad puppy eyes.
I know exactly what you mean.
It's like she's saying, hey, I was expecting that deliciousness,
Right.
and now I'm feeling disappointed.
Yeah. And that kind of reaction goes beyond just a simple reflex.
Yeah.
It suggests an awareness of their own expectations and a capacity to feel those negative emotions when those expectations aren't met.
So we're looking for these subtle but telling signs in their behavior. Signs that point to a level of awareness and cognitive complexity that goes beyond just reacting to the world.
Absolutely. And when we start looking at the animal kingdom through this lens, we might be surprised by what we find.
Yeah.
Because it turns out that consciousness might be more widespread than we ever imagine.
Okay, are you telling me we might find consciousness in creatures
It's possible.
we wouldn't normally consider?
Yeah.
Like, are we talking insects? Fish? Where do we start drawing the line?
That's the question.
Right.
And to really dive into that, we need to look at the evolutionary history of consciousness. And that's where it gets really mind-blowing.
All right, lead the way.
Let's do it.
I'm ready to go deeper into this evolutionary rabbit hole to see
Okay.
where it takes us.
Awesome.
All right, let's do it.
Let's go.
So we're talking about the evolution of consciousness.
Mm-hmm.
It's mind-blowing to think that something as complex as subjective experience could have evolved.
Yeah.
Where do we even begin to trace that journey?
Well, the amazing thing is that consciousness doesn't seem to have just appeared once.
Okay.
Feinberg and Mallatt suggest that it actually evolved independently multiple times in different branches of the animal kingdom.
Hold on. Multiple times.
Yeah.
So you're saying that a fish, an insect, and an octopus
Mm-hmm.
might have all arrived at consciousness through completely different evolutionary pathways.
That's right. We see evidence for it in vertebrates like us, but also in arthropods like insects and cephalopods like octopuses.
That is wild.
Yeah, and the fascinating thing is their brains look completely different.
Right.
It's like evolution found 3 unique solutions to the same problem, navigating a complex world.
It's like they're all playing the same song
Right.
on completely different instruments.
Yeah.
But if their brains are so different, how can we even compare their experiences?
Mm-hmm.
How do we know they're experiencing anything at all?
That's where those isomorphic maps we talked about come into play.
Okay.
Remember, those are the brain's way of creating internal representations of the world, those point-by-point neural maps. Right. While the specific brain regions involved might differ, the basic principle seems to hold true across these different groups.
So even though an octopus brain looks nothing like a human brain,
Right.
they might both be creating similar kinds of internal maps, just using different neural hardware.
Exactly. And one of the most striking examples of this is in the evolution of mental imagery, specifically vision.
Okay.
Let's take a trip back in time to the very beginnings of vertebrate evolution,
Okay.
to those ancient fish swimming in primordial seas.
Fish. Really? I wouldn't exactly picture a fish having vivid mental imagery.
I know it seems counterintuitive, but bear with me, because fish brains actually offer some incredible insights into the origins of consciousness, especially when it comes to those internal maps.
Okay, what's so special about fish brains?
Well, they have a brain region called the optic tectum,
Okay.
which is a key player in processing visual information.
Okay.
It receives input from the eyes and creates a kind of spatial map of the visual scene. Think of it as a rudimentary version of those isomorphic maps we talked about earlier.
So even a fish has a brain region that's dedicated to creating a representation of its visual world, kind of primitive mental image.
Exactly. And this map is crucial for the fish's survival.
Okay.
It allows it to track prey, avoid predators, and navigate its environment.
So it's not just about seeing, it's about understanding the spatial relationships between objects and using that information to make decisions.
Precisely. And the optic tectum doesn't just process visual information in isolation.
Okay.
It also integrates input from other senses like touch and hearing.
So it's like a multisensory hub creating a more holistic representation of the world.
Ah.
That's pretty impressive for a fish brain.
Right. And here's where it gets even more interesting.
Okay.
As vertebrates evolved this ancient structure, the optic tectum didn't just disappear.
Okay.
It became a foundation for the development of even more complex visual processing centers in the brain.
So our own brains, with all their sophisticated visual processing power, are actually built upon this ancient system that first evolved in fish.
It is pretty amazing.
That's a pretty amazing thought.
It really is, and it highlights how evolution often works by building upon existing structures, adding layers of complexity over millions of years.
Okay, so we have the optic tectum in fish.
Yep.
What about amphibians? Did they inherit this same structure?
They did, and in amphibians, the optic tectum continued to play a key role in vision and multisensory integration, allowing them to navigate their increasingly complex environments.
And what about reptiles and birds? Did they follow a similar path?
Absolutely. The optic tectum remained a key player in their visual processing systems as well.
But something must have changed along the way, right?
Yeah.
Because our own visual experiences are vastly more complex than those of a fish or a lizard.
You're absolutely right. The big leap came with the evolution of mammals.
Okay.
In mammals, a new brain region took center stage,
Go on.
the cerebral cortex.
Ah, the cerebral cortex.
Yeah.
The big wrinkly part of the brain
Right.
we always see in pictures.
Of-
That's where all the higher level thinking happens, right?
That's right. And it's this expansion of the cerebral cortex that allowed for the development of much richer, more detailed mental imagery.
So instead of just having a basic spatial map of the world, mammals could start creating those vivid, colorful, multi-layered mental images
Yeah.
we associate with conscious experience.
Precisely. And the key here is that the cerebral cortex didn't just replace the optic tectum. It actually built upon it integrating those ancient spatial maps into a much more complex and sophisticated system.
It's like evolution took the basic blueprint of the optic tectum and said, okay, let's add some bells and whistles, some high-definition color, some surround sound, and see what we can create.
That's a great analogy.
So we've traced the evolution of mental imagery from those rudimentary spatial maps in fish all the way to the complex visual landscapes we experience as humans.
Yeah.
It's amazing to see how those ancient systems are still at play in our brains today.
It really is a testament to the power of evolution, to tinker and refine, to build upon existing foundations, to create something truly extraordinary.
But remember we said that consciousness didn't just evolve once.
Right.
What about those other groups, those arthropods and cephalopods?
Right.
How did they arrive at consciousness? Did they also go through this same optic tectum to cerebral cortex evolution?
That's what makes this whole story so fascinating, because it turns out that arthropods and cephalopods took completely different routes to consciousness, developing their own unique ways of processing sensory information and creating those internal maps.
Okay, now I'm really curious. Let's start with arthropods.
Okay.
They're about as different from vertebrates as you can get, right?
Yeah, they are.
How in the world did they develop consciousness?
It's a real testament to the diversity of life and the power of evolution to come up with creative solutions. Arthropods, despite their radically different body plans and nervous systems, still exhibit many of those behavioral signs of consciousness we talked about earlier.
You mean things like global operant conditioning, behavioral trade-offs, and frustration behavior?
Exactly.
But their brains don't have anything resembling a cerebral cortex, do they?
Nope, not at all.
But that doesn't mean they can't create internal representations of the world.
Right, that's right. Feinberg and Mallatt highlight a brain region in arthropods called the central complex, which seems to play a crucial role in processing sensory information and creating a kind of internal map, although it's structured very differently from the optic tectum.
So it's like their version of the optic tectum,
Yeah.
but built from a completely different set of neural blueprints.
Exactly. It's like two different chefs coming up with their own unique recipes for the same dish.
Right.
And just like with vertebrates, we see evidence of this spatial awareness in their behavior.
Yeah.
They can navigate complex mazes, remember the locations of food sources, and even exhibit signs of planning and foresight.
It's mind-blowing to think that something as tiny as an ant might be creating a mental map of its world, planning its foraging routes.
Right.
And maybe even feeling a sense of frustration when things don't go according to plan.
It really challenges our assumptions about where we might find consciousness in the animal kingdom.
Totally.
And if insects can do it, imagine what cephalopods with their incredibly complex brains might be capable of.
All right, you've definitely got me hooked.
Oh.
Let's talk cephalopods.
Okay.
They're like aliens from another planet with their tentacles and ink and those incredible color-changing abilities.
They're fascinating creatures.
What's going on inside those squishy heads of theirs?
Well, get ready for another dose of evolutionary wonder.
Okay.
Because cephalopod brains are unlike anything we've seen so far.
Okay.
They're incredibly complex and capable of some truly remarkable feats.
I mean, we've all seen those videos of octopuses escaping from jars and solving puzzles.
Right.
They clearly have some serious brain power going on.
They do.
But how do they create those internal maps? What's their version of the optic tectum or the central complex?
That's the thing. It's still not entirely clear. Cephalopod brains are so different from ours that scientists are still trying to unravel their secrets.
Wow.
But based on their behavior, which is incredibly sophisticated, it seems very likely that they have some way of creating internal representations of the world.
Right, because those puzzle-solving skills and escape artistry aren't just random, lucky behaviors.
Right.
They suggest a level of planning, problem-solving, and spatial awareness.
Yeah.
That points to a conscious mind at work.
Exactly. And Feinberg and Mallatt propose that instead of relying on a single centralized processing center like the optic tectum or the central complex cephalopods, might use a more distributed network of brain regions to create their mental images.
So it's like their mental movies being projected across a network of interconnected screens rather than on a single big screen.
That's a great way to visualize it, and this distributed approach might actually explain why cephalopods are so adaptable and flexible in their behavior.
Oh, okay.
They can change their body shape, color, and texture in an instant to match their surroundings. They can learn new tasks quickly and solve complex problems using tools.
It's like their minds are less constrained by rigid structures.
Yeah.
And more fluid, more adaptable to changing circumstances.
Right.
It's almost like a different kind of intelligence altogether.
And that brings us to another fascinating question.
Okay.
If consciousness can take so many different forms, what does that tell us about the nature of subjective experience itself?
Right.
Does an octopus experience the world in the same way a human does?
Yeah.
Or is it something altogether different?
Those are questions that really make you ponder the vastness of consciousness and the limits of our own human understanding.
They do.
But before we get lost in those philosophical depths, I'm curious about something else.
Yeah.
We've talked a lot about those external senses and how they contribute to consciousness. But what about those internal feelings, those emotions that we talked about earlier?
Yeah.
Do those also play a role in the evolution of consciousness?
Absolutely. In fact, some argue that feelings are the very foundation of consciousness, that without the capacity to feel, there would be no subjective experience at all.
Okay.
And just like with sensory perceptions, those feelings have their own evolutionary history, their own story to tell.
Okay. I'm ready to dive into the world of emotions.
Okay.
Let's shift gears and explore how the brain creates those subjective experiences of joy, fear, anger, and everything in between.
Let's do it.
Okay, so we've explored how those mental images, those internal maps of the world evolved over millions of years. But what about feelings? What's the evolutionary story behind emotions like joy or fear or anger? How did those come to be a part of the conscious experience?
Well, it's fascinating to consider, isn't it? Because unlike those neatly mapped visual representations that we've discussed,
Right.
the brain structures responsible for feelings are a bit more diffuse, a bit more mysterious.
So no clear GPS coordinates for happiness or sadness, no single brain region that we can point to and say that's where fear lives.
Not exactly, but that doesn't make them any less real or any less powerful.
Right.
In fact, some argue that feelings are even more fundamental to consciousness than those sensory perceptions.
Right.
That without the capacity to feel, there would be no subjective experience at all.
Wow, that's a pretty bold statement.
Yeah.
So if we can't pinpoint a single feeling center in the brain,
Right.
where do these emotions come from? What parts of the brain are we talking about?
Well, it's definitely not a solo act.
Okay.
It's more like a symphony of brain activity with multiple regions working together to create those complex emotional experiences. But there are a few key players that Feinberg and Mallatt highlight.
Okay.
One is the amygdala,
Go.
a small almond-shaped structure deep within the brain. It's often called the fear center because it plays a crucial role in detecting and responding to threats.
So when I jump at a sudden noise or feel that surge of adrenaline when I see a spider, that's my amygdala.
Yeah, that's your amygdala kicking into gear.
Kicking into gear.
Yeah, exactly. It's constantly scanning for potential dangers and triggering those fight or flight responses that have been so crucial for survival throughout evolutionary history.
Makes sense. But what about those positive emotions? The joy of a delicious meal, the excitement of a new discovery, the warmth of connection with loved ones. Where do those come from? Do we have like a happiness center tucked away somewhere in our brains?
I wish it were that simple.
Right.
There isn't a single happiness headquarters, but there's a fascinating pathway called the medial forebrain bundle, or MFB, that plays a big role in those feel-good moments. It's a bundle of nerve fibers that runs through the middle of the brain and is associated with feelings of pleasure and reward.
So it's like the brain's reward pathway.
Exactly.
Like, yes, do that again.
Yeah.
That feels good.
That feels good. And it's not just about basic needs like food or sex. The MFB is also activated by things like social interaction, music, learning new things, even just the anticipation of something enjoyable. It's what keeps us motivated, engaged, and curious about the world.
So when I'm listening to my favorite song or dancing with friends or having a good laugh, it's my MFB lighting up, showering my brain with those feel-good chemicals.
That's exactly right. It's what makes life worth living, right?
Right.
But it's not just the amygdala and the MFB running the emotional show.
Okay.
There are other important players involved as well.
Like what?
What other brain regions are contributing to this emotional symphony?
Well, there's the hypothalamus, which plays a key role in regulating basic drives like hunger, thirst, and sleep.
Right.
And there's the insula, which is thought to be involved in processing bodily sensations and generating those gut feelings.
Right. So it's really a whole network of brain regions working together, each contributing its own piece to the puzzle of our emotional lives.
And just like those visual systems we discussed, this network has evolved over millions of years, shaped by the demands of survival.
Because emotions aren't just about feeling good or bad.
They also serve a very practical purpose, don't they?
They do.
They guide our behavior,
Yeah.
help us make decisions,
Yeah.
and ultimately increase our chances of survival.
Precisely think about fear, for example.
Okay.
It might be an unpleasant feeling, but it's what keeps us safe from danger.
Right.
It's what motivates us to avoid risky situations or to fight back when threatened.
And what about those positive emotions? What evolutionary role do they play?
Well, they're what drive us towards things that are good for us.
Okay.
The joy of a delicious meal ensures we get the nourishment we need. The excitement of a new discovery encourages exploration and learning. The warmth of connection with others strengthens social bonds, which are crucial for our well-being and survival as a species.
So it's like emotions are the driving force behind so much of our behavior, whether we're consciously aware of it or not.
Absolutely. They're deeply ingrained in our biology, shaped by millions of years of evolution.
And just like with those internal maps,
Uh-huh.
I'm guessing we can see signs of this emotional complexity in other animals as well, right? It's not just a human thing.
You're absolutely right. Remember those behavioral cues we talked about earlier? Things like global operant conditioning, behavioral trade-offs, frustration behavior. Those not only suggest consciousness, but also point towards the capacity for emotional experience in other creatures.
So a fish feeling frustrated when it can't get to that tasty worm, a dog experiencing joy when reunited with its owner, an octopus, showing curiosity and playfulness while exploring a new object.
Exactly. It might sound strange to attribute such complex feelings to creatures so different from ourselves,
Yeah.
but the evidence suggests it's a real possibility.
It really does make you reconsider our place in the animal kingdom, doesn't it?
Yeah.
We often think of emotions as something uniquely human, but it seems like we're not so special after all.
I think that's one of the most profound takeaways from all of this. Recognizing the potential for consciousness and emotional experience in other animals opens up a whole new world of understanding and empathy.
It's a humbling thought, isn't it? It reminds us that we're all part of this interconnected web of life, each experiencing the world in our own unique way, driven by those same basic needs and desires.
Exactly. And who knows, maybe by studying the diversity of consciousness and emotion in other animals, we can gain a deeper understanding of our own inner worlds.
This entire deep dive into consciousness has been incredible.
It has been fun.
We've explored what it means to be aware, delved into the brain structures that make it possible, traced its evolutionary journey across the animal kingdom, and even pondered the nature of subjective experience itself.
We've just scratched the surface.
Right. It's amazing.
There's so much more to explore.
And for me, the biggest takeaway is that consciousness is not this mystical, intangible thing.
Right.
It's a product of evolution,
Yeah,
shaped by the demands of survival, and deeply rooted in the biology of the brain.
it is.
And it's likely far more widespread than we ever imagined.
Absolutely.
And while we still don't have all the answers, it's exciting to see how science is shedding light on one of the biggest mysteries out there, the mystery of subjective experience, of what it means to feel, to perceive, to be alive.
It really is exciting, and it makes me wonder
Yeah.
if consciousness can take so many different forms, what other kinds of awareness might be out there waiting to be discovered? What other mysteries of the mind are yet to be unveiled?
That's a great question to end on. And for all of you listening, I encourage you to keep exploring this fascinating topic. Consciousness Demystified by Feinberg and Mallatt is a great place to start.
Great book.
It'll challenge your assumptions, expand your perspective, and leave you pondering the wonders of consciousness long after you finish the last page.
Absolutely.
So until next time, keep exploring, keep questioning, and keep diving deep.
See you next time.